All right, can you hear me? Can you hear me? All right. So what we are gonna do today is to talk about the potential that you have seen before, the relationship of the potential to the electric field. And then we will go to surfaces like conductors. We'll see how fast we are gonna do this. But before we go there, I would like to summarize for you so you remember it. The types of fields we have found from different types of sources. All right, so again, we have said this before, we're gonna summarize it again. When your source is a point charge, then the electric field varies as 1 over the distance squared. Here we write it, you see a cube there because I have an R in the numerator. All right, this is the exact way to describe it. But when you talk about this, you're gonna say the field varies as 1 over the distance squared from the point charge. When you go to an infinite line charge, it goes as 1 over the distance. We write it like this because, you know, we have the vector and then that's the correct way of writing it, but in reality it tells you the magnitude goes as 1 over the distance. From and distance, if you have an infinite line charge, it's like, you know, the point that connects me and the line that goes perpendicular to that infinite line, all right? That's distance. If you have an infinite surface charge, then it is constant, all right? The field does not vary with distance from that infinite plane that is charged uniformly. All right, and this is the last one is the charge sphere. So a charge that distributes over a sphere. Why do I call it always dielectric? Because in reality, charge cannot exist in places uniformly without something sustaining it. And usually if charge is distributed uniformly, it's on a dielectric. All right, that's why most of the time you'll have that. Okay. Now, the other thing that we did last time, let me think, was, no. What is that? Okay. Let me see here. Okay, wait a second. All right. From various sources. What did I do? Okay, I have it somewhere, but it's definitely here. So on Monday, we will go to modules, module 3. Module 3. Okay. Okay, we did that. At the end, last time, what did I, it's like, what? Okay, I'm looking at the wrong place. that was Monday. Yeah, so why am I looking the wrong place? All right, so we did this last time, okay? And I have all of the details here. We talked about this, the square. We talked about how the field, when it's at the center of the square, is 0, right at that point. And then as you go along this direction, changes, all right, as a function of z. And then what we had after that was a circular charge that we wanted to cover, which I don't have here, but I will now figure it out there. I was looking at, I need to look with, I was looking at the wrong week. All right, so now, there, before we go there, I wanted to also, which I will give it to you as a problem, but I would like you to start thinking about the following problem on the basis of what we have seen so far. So I'm gonna add a page, and I will move this page here. Okay, so now let's assume that we have a circular charge. So it is like a loop. It's like exactly a circle, all right? And I would like to find the field on this one at the center, first of all, here at point B. And then if this is the z direction, I would like to find it along the z direction as I move away. All right, so how we are gonna do this here, exactly the same way we did it for a finite line charge. So we are gonna take a small section here, and we'll say, okay, if this is dl, ql, yes.
Is this a ring or is it a solid disk?
No, it's a ring. It is a ring, like a thicker. All right, only a ring. And then, so from this charge, it's gonna, the field, say somewhere here at the center, it's gonna look like this. You agree? Now, I can find the diametrically opposite charge, green here, which is gonna be along this direction. All right. Both of them the same, dl, q sub l. And then that is going to exert a field at the same point O, which is the center. Okay, O is this one. The center of the circle is going to exert a field that looks like this. And it's going to be the same, equal, because the radius is the same. The distance from the center of the circle is the same. The decibels are identical, all right? The two little charges are identical, same charge, but in opposite positions. So we're looking at the center, and the field there is how much? 0. You remember when we had 2 point charges that were identical, that we found that the field at the along the line that connects the two charges in the middle was 0? Same thing here. So if you take all of the other points around, and you find for every point, you find for every charge, point charge, which is like a DLQL, you find the diametrically opposite, then all of those, all right, the whole circle will be made out of pairs of those DLQL, all right, charges, which are diametrically opposite. And therefore, the total field at point O is 0. So if this is Z, so I can say the total E at Z equals 0 equals 0. All right, what happens if we go a little north of Z equals 0? So let me erase those. I will keep the two diametrically opposite charges, and then I will do this for one, that field, and I will do this for the other, that field. Okay. Now, this field is, of course, not along the z direction. Has the direction of those lines that connect that point along the z-axis here with each one of those charges. So it's going to have two components. That field is going to have each one of those. The blue and the green will have two components. Each one of them is going to have a component along the z direction, and will have components along whatever horizontal direction. All right. So for example, this E here is going to have two components. One like this and one like this. Do you agree? The blue. And the green is going to have also two components. One like this and one like this. What is going to happen then with the two components? Which ones are going to cancel out? This, yeah, the horizontal, this, and this will cancel out. So what happens along the z-axis? The electric field is going to be along the z direction, and of course, it's going to grow as it goes away from zero. However, think of the following. What if then I go into a very long distance? All right, very long distance from this. So if I move very far away from this little circle, so it's going to look like this, and I will be out here. This little circle is going to be like a point charge to me. All right, so for example, if I draw a circle here, like that, here, and I ask somebody from that side of the room to find the field from this one, all right? And then if I have here, this is the radius R, and I have here Q sub L, the person down there is gonna see not a circle because it's so far away. The person down there is gonna see like one dot, all right? Which is gonna have a total Q equal to 2 pi R Q sub L. So this far away is gonna look like a point charge. So if I go this far away, how is the field gonna change with respect to the distance from that? As 1 over distance squared. So what is gonna happen with all of these fields, like the square we had last time and the round, that it starts at 0, then it grows for some time, comes to maximum, and then it goes down. Softly though. I mean, it is not gonna have a discontinuity, all right? Or in the field or in the derivative. It's gonna be a soft change from 0. So it's gonna, if you go far away, you're gonna see the field. Let me increase that a little bit so you can see it. So let's assume it's this one. So if I were to plot the field here, it will go from 0, let me plot it like that. Will go from 0 to a maximum, and then it's gonna go away as 1 over the distance squared. And that's how the field is gonna go along the z-axis. Okay, that is characteristic of both the square and of the circle. All right, so you remember that because they are finite in size, they are not infinite. So when you are very close to the circle or the square, you see a different variation with regards to z. But as you move away, you see what you would normally see for a charge, for a point charge. Now, let me ask you another question. As part of this problem, of the first one, let's assume now, then instead of a full circle, I have a half circle. All right, I'm gonna give you then, instead of a full circle, let's assume that I have a half circle like this. All right, just half of what I had before. And that it looks like on the plane of the circle, but if I were to do it like before, it would look like this somehow, but it's gonna be a circle, all right? It's just that in 3D, looks like that. Okay, let's assume that I cut the circle in half and I throw half of it away. And the rest remains the same. So for example, if I write the rest here, it's gonna look like this, all right? And here. And then let's see what happens now, because I only have half of the circle. Okay, so I'm taking this side, this one. DL here, and then times Q sub L, that is the charge which is infinitesimally small at that point. And then I'm looking at this point O here, this is it. And then at that point O, the electric field goes like this from this charge, okay? And then let's assume now I don't have the diametrically opposite charge. So the only symmetric that I have is another charge here on the other side, which is identical, but somehow symmetric along this axis. I don't have any other symmetry here. So this one is gonna move like this, but the field is gonna be here. Okay, so what happens here? Even if I am on the surface of the circle, the field does not become zero because half of the circle is gone that was canceling out, all right? So now the field here, if this is on the surface of the circle, if this is say the X direction, it's gonna have two components, all right? One from here and the other from the other side. They will sum up to give one component. Let me put it this one here. They will give the two together. They will give one component that looks like that. Okay, so it's going to have one component along the X direction. What is going to have along the Y direction? If this is the Y, what is going to happen with the Y components? Cancel out, because one of them goes like this down, the other goes like this down. All right, so they cancel out. So this one has one component along the negative X direction. What is going to happen if I go vertically up? See, if I start going along this direction.
Same thing as before, this time you have the field of the X direction as well.
Minus X, perfect. Exactly what your colleague said here, as you move up, the same thing, the Z component, all right, is gonna be there only, but then you're gonna have an X component along the negative X direction. So why I do these problems like that? Because if you do it like this before you start writing your equations, you're gonna know what you're looking for. Because now you know you're looking for two components. One is sub Z and the other is minus E sub X, like along the negative X. If you know that it's, then you know what you're looking for, and if something else comes out of your calculations, you know it's not correct. And that's how you always have to solve problems. Try to make sense out of what they're asking you, okay? So, having said that, this brings to a closure. I'll put all of this information on your Canvas. We are moving now to potential. Okay, do you remember how we define potential from your physics classes?
Difference between
Yes, but what is this difference? What does it really mean? What is the think physics? All right. Yeah, let's think a little more. When think potential, the way we use it in real life. When I say student A or faculty A has more potential than faculty E, what does that really mean? It means something, it has a meaning. What does it mean to you?
Somebody else is better than somebody else. Somebody else.
Potentials.
Well, they have to-
Aha. Remember, potential does not mean they are better now. It has the capability of becoming better. Okay. What does potential mean in mechanics? I have I move a bucket of water up, all right? Yeah, it's what happens. So I move a bucket of water up, you know, like you do in the wells, the old wells. You turn that and then it moves the bucket. What happens when you move the bucket? The bucket was down at the bottom of the well, and that well, we say, was in equilibrium. Nothing was happening. All the forces were neutralized. They were neutralizing each other, right? All the forces at the bottom of the well. Now then, of course, it's filled with water. It doesn't matter. It was at an equilibrium. Then you just pulling it up and you put a lot of energy to do this. So when it comes up on the well, what do you say? That it has a mechanical potential. What does that mean? That if I let it loose and I don't put an effort, it's gonna go down all the way, which means it's gonna release back all of the energy that I used to pull it up. In fact, that's how we make plants today, all right? In converting energy, some mechanical energy to electric energy. That's how we do things. I mean, we transform energies from one domain to another. By using this, we add energy, we create potential, and then we use the potential, we transfer it into something else, all right? Okay, so electric potential. What is the electric potential? Is the work that we have to do. When, for example, I am inside an electric field, okay, and let's assume now that I am inside some kind of an electric field that was created by another charge. I don't care about this other charge, but I am somehow inside that field. And let's assume that this field here is like this. All right? Don't care. I know who created it. I know that it's there. And now I have here another charge. Which charge somehow is kept at this point at equilibrium, and it's not going to look like this, let me tell you. That's not necessarily how it's going to look if I put another charge. Okay, so let me just tell you this now, because this is a wrong picture. Depending on the other charge, the lines will change. Okay, and as a matter of fact, I don't want to make it complex, but let's assume that I would put another charge in there, I place it, and then I want to move it. And in fact, I don't want to have that and then somebody says that I did the wrong thing. So let me do it correctly, all right? I don't want to simplify too much that is unreal. Okay, so let's assume that you have this charge here, Q1, and this charge here, Q2. And Q1, 2, or Q and Q. Do you remember the lines that are created? Let's also do some review. The lines, do you remember how they will be? Okay. That's how practically the, not the lines of the field, but the lines of the, that's how the potential is going to be more or less. But if you want to know about the field, it's going to be 0. As a matter of fact, why do I not? Well, sorry. I did not have that as an example, so I have not. But I will say, let's do it more lines of the field. So it's going to be like this. Oops, no. Like this. and like this, and like this. Okay, that's how the lines will be. The other lines were not incorrect, were just not the electric field lines. So that's how the lines will be, all right, from the two charges, because they are identical. Now, let's assume that within that field that has been established, and now it is in equilibrium, all right? So that's, you put two charges like that, they will be like this, you don't touch them. Let's assume that I'm gonna take this one charge and move it. And move it from there to another location, all right, up here. And let's assume that I wanna move it from here there, all right? To be able to do that, I have to do work. It's not gonna happen easily. I will have to put energy into the system because I take it from equilibrium and I move it in another state where it has to reorient itself for another equilibrium. To be able to change one system from one state of being to another state of being, you have to add energy into it. All right, so that work. So work is something you do over time at a particular point in time. What is energy? The integral of work over time, all right? That's the difference. Work is what I do now at this point in time, and then at next point in time, maybe more or less, and then the following. So it varies with time. But if you wanna find the overall work, you take the integral, and then we talk about energy. But the work is gonna be for this, and especially if the distance is very small, let's assume that this is indeed a small distance, it would have been work is going to be infinitesimal work, all right? If I move it by an infinitesimal distance, and if I divide that by Q, it would give me a new entity, which I call the potential, all right? But in fact, what I want to do is when I want to find the total amount of work, so I will have to integrate along this path. And what that gives me, as a matter of fact, is very interesting, because if I go and integrate over this path, I'm gonna find over the path from, say, point 0 to point A to point B, I will find this integral. All right, and then I still have one charge. I do it like this. How much is the work that I put now to move this charge is related to the force that is exerted between the two charges. All right, and of course the force changes every time I move it along. So this one is a function of the electric field that I have to integrate from point A to point B, all right? And we call this, if you go here, we call this the potential difference, if you like, between the 2 points, all right? So if I move from one point A to one point B, this integral of the work that I have to do divided by Q, we call it the potential difference between the 2 points. And why is that? Because the potential shows energy accumulated. All right, that's what it shows, energy accumulated. So if I have 2 points in space, more energy up here, less energy down there, then to move from the higher energy to the lower, I release energy. But if I want to go the other way around, if I am at the lower energy level and I want to go to the higher energy level, I need to absorb energy. All right. And that's why those, we call them potential. We call this function the potential. We introduce this concept of potential to explain that. And the way we introduce the concept of the potential is through this relationship that shows in reality the potential is nothing else, or the electric field is nothing else. It's better to define like that. The electric field is nothing else, but in reality, the derivative of the potential, the difference, if you are at a distance dz, then it's going to be almost the derivative of the potential. The way the potential changes locally is going to be related to the electric field. The way the potential changes between 2 points further away, it will involve an integral, of course. But this function here is a differential function, right? Differential, it applies at 1 point in place, 1 point, which means at that point in place, the electric field is nothing else but the derivative of this new function, which we call the potential. And then what this new function shows in reality, it shows what is the difference of energy levels between 1 point and another point I'm trying to go to. All right. If it is a differential relationship, it tells you how much is the change of the potential at that point, like the derivative. All right. So if I am over a distance dz, which is a small distance, it's between 0.1 and 2. All right. This is going to be dz. And of course, then we're going to have, if this is v1 and v2, we're going to have that v2 is going to be v1 plus dv. All right, that's what it means. If I am at, it's very, very close, the 2 points, that I go from one to another by a distance dz, then these 2 points will have 2 potentials, and the difference between these 2 potentials divided by dz is practically the electric field with a negative sign. All right, this is how we have introduced it. But you remember, the potential is nothing else but a measure of the energies that are stored in the system. If it's an electric field, the potential, the electric potential tells you how much energy is stored in that electric field at different points. All right, that's how you need to consider it. Now, the difference between the potential values at 2 different points, we call that the voltage. And we use that in circuits. All right, so well, a circuit, a line that carries, for example, a current, which is like a moving charge with a constant velocity, is nothing else but a system that excites electric fields. All right, so if you take a line that is connected to a battery, so here, let's assume that you have a line like that, and then I have a resistor. Usually what happens, what is gonna move through the, we're gonna see that later, but I wanna check right now because the concept is a little, we have not covered it at least in this class. But when I have a battery connected to a resistor, I show a current, battery is usually plus here, which means that I have a lot of positive charges accumulated there. All right, and then the other side is connected to the ground, which is a sea of infinite negative charges. We talked about that. So now I have a resistor which connects to a lot of positive charges here, a lot of negative charges there. What is going to happen if I have positive charges on one side of a conductor, negative charges on the other side? Which charges are going to flow? The electrons, negative charges flow. The real current is the electrons, caused by the electrons, but in circuits, we show the opposite. We have decided that our current is going to be along the direction of the positive. This is an agreement we've made, all right? So, what happens here? Where is the highest potential? And what happens when the current flows? We say that V1 minus V2 divided by R, resistor there, gives I. All right? So practically, because there is higher electric potential at one side of the wire less electric potential or zero since connect to ground. At the other side, this difference is forcing an electric field to be excited. All right, and we indicate the current, which is, the result of the moving charges. We indicated, we have decided to indicate like that, even if electrons move the other way. Okay, so now you see the potential, we're using the electric potential here, which in fact we see it as a voltage all the time. We only see an electric potential when we are going to ground, we say zero. Okay, otherwise, we don't speak very much about electric potential. We talk about the voltage. Even when we have a battery, we talk about the voltage, 12 volts, say, 1.2 volts, for example. Meaning from the ground, which is zero, V1 is 1.2 volts. But in reality, we talk about voltage drops, all right? But the potential is what you really have exactly the same way we see it if the electric field expands in 3 dimensions. Okay. Now that we have said that, I want to see what time we have. 2:30. Okay. We are going to introduce something also interesting. And here is something that I will have to draw it, and then we're gonna go back into it next time. But I want to draw here something for you as a preliminary thought. So let's assume that I have a perfect conductor. And this perfect conductor is like a sphere. All right. And that sphere is in equilibrium. Nothing excites around it. There is no charges anywhere. It just sits there. Electrically is neutral. Then I apply an electric field. Okay, let's assume that the electric field looks like that initially. All right, and then I bring this electric field, and in this electric field, I bring the sphere. What happens then? So the electrons inside the sphere is a perfect conductor. What does it mean to be a perfect conductor? You have a lot of free electrons, a lot. Even if you just, take a piece of cloth and you do it like that, you increase the temperature. What happens when you increase the temperature? A little bit, and a free electron needs a little bit to escape from the atom. So even with higher temperature, you have a lot of electrons that flow around. Now, if there is not a sustained electric field to give them some direction, because what happens when you have a charge inside an electric field? The force that applies to it is going to push it in one direction. And usually, what happens if you have an electric field and you throw an electron here? If you throw an electron there, the electron will go along the direction of the electric field. All right, we don't do that here. I just wanted to remind you. But here we have this conductor and has a lot of free electrons. All right. When they see this, that electric field is excited by what? From what we've seen, what kind of a source? Probably a point charge somewhere very far away, like an antenna that I see as a point charge, all right? So somewhere far away, there is a charge like this. And as a matter of fact, if I want to bring it even closer, I will do the lines more realistically. I will say from this charge, the lines go like this. Do you agree? All right. So, and then when they come here, these charges see the electric field. What happens when all of these electrons see the electric field? The fact that you have a positive charge there and a negative, they will go as close inside the conductor as they can to the positive charge. All right, as close as they can to the positive charge. So practically here in the conductor, they're gonna all crowd there. all right? All there. And what is going to happen if they all crowd there? What's going to happen to the opposite side of the sphere or to the sphere in general? There are going to be some holes left over. And those are going to be positive charges. So then you're going to have positive charges here and wherever, depending on the problem, they will be here. But usually all of the charges will not stay inside the sphere. They will go directly to the surface. Because see, I do them like this here just to be able to show how many they are. But in reality, all of the negative charges will be on the surface and all of the positive charges, the holes, will be on the opposite side of the surface. All right. So what is going to happen here is that the electric lines here will look like this. All right. They will bend to go and stop on these charges. And from here, we're going to go out like that. So practically, if you have an electric field and you put a conductor, it bends the lines. A lot of times that's a problem when you have a conductor, a large conductor like a ground, all right? And you put this into an electric field because it's gonna disturb it. Now, when, and then you try to, of course, ground it, all right, at some point, and you see what happens when you ground it. So in any case, remember that if you have an electric field and a conductor, the electrons will flow on the surface of the conductor. So practically, if I wanted to show here correctly, I will put them all one on top of the other and very close to the surface. I will have here more here and there. And then I will do the same thing with this. So I will put them like that. What happens inside the conductor? Since all of these charges have moved to the surface, what happens inside? Zero charges. What happens if there is zero charge to the electric field? These charges do not see each other, first of all. All right. So it's like, I was trying to say, it's like you have a team, and then you move, the team is like white shirts, red shirts. All right, and then you take all of the white shirts in one room, the red shirts in another room. They don't see each other. Okay, you don't know if they exist or if they have gone away. All right, so it's like you have separated those and they don't see. They are not impacted by each other. They are impacted only by the fields outside. So inside a conductor, the electric field is zero because there are no charges. And because those charges on the surface, they don't care about what happens behind them. They're looking to the outside to see what happens outside of the sphere. So this is zero. This is true with every perfect conductor. So another example is to have an infinite plane and then have a charge here. All right, let's say a positive charge. So all of the negative charges, the electrons, will come here. And if that conductor was infinite long, the positive charges will go someplace. You will not even see them nearby. All right, but if it's a finite here, it's like a finite piece of metal, for example, then all of the positive charges will be there. Okay. But it's metal and it's zero here. All right, you remember, inside the conductor, zero field, so you don't see anything. And the charges don't see each other, which is kind of interesting because also they distribute themselves differently since they don't see each other, right? They will only react to the field outside. All right, so these are the things we are gonna start thinking. This is very important for shielding. Because, for example, if I wanna have a charge and I wanna shield this metallic sphere, ground the outside of the sphere, I cannot shield the charge inside. That's why for you, when you are in the lab and you have coaxial lines, like the ones, for example, if you use them for some, that they have a conductor inside and the conductor outside, you have to make sure that your connectors ground the outside. Otherwise, you're going to have a field everywhere. And if you have wires or you have connecting cables, all right, that are not shielded well, then practically what happens, all of these electric fields will mix up with everything and things are not going to work. So you're going to lose a lot of power in your circuit, or you're going to see some things that you will not recognize, all right? So a lot of times grounding and shielding is extremely important, because then you need to stop your field from expanding outside in other spaces where the field is not needed. Yes. No, you know what you do? No, you put here a ground. Oops. You go there and you put a ground. This ground is an infinite sea of electrons. What happens to these electrons when they see a positive charge? They all come up here and they go around and neutralize the positive charge. You only need one wire. And of course, if it's very long, you need to put it in regular spaces, but you need to only ground the outside. And then you take care of that. All right, we're gonna see that more next time. Now, with this, I want to say that I'm gonna give you an exercise for Friday. Is that, well, Wednesday today, okay? They seem the same. For Friday, you're gonna have an exercise and I will activate it right now. Okay, and you will see the exercise. We have already talked about this here. Let me see that. Okay, this one, you see that? That one, you're gonna have an exercise and you are gonna have to say which components of the field is that you have here. And I will assign it. And it's gonna be for Friday, until Friday morning. The Y component. It does not have Y component. I will have circle. It says X. Yes, so all the horizontal components in the half circle. Okay. So in the half circle, okay. This one, so this one is gonna, if it's up, all right? I don't have it here, but this one, if it's higher, so here, this one, and then say this one, all right? So if it goes like this, that is gonna go like that, and it's gonna have a Z, it's gonna have an X, and it's gonna have a Y, all right? But then, so Y, X, X, Y, and Z. I mean, I think the X is negative, so it's minus X here, all right? So the X is the other direction. So, and then this one is gonna have a Y, an X like this, and a Z. So the Y's are canceled out. So because they are symmetric along that direction. Okay. Yeah, sure.
So I emailed you about quiz 3.
And then I was still using with like a hoodie on,
We go on
like shoes.
I don't know. I mean, I was showing to one of your colleagues. When was
I
the
don't
last
know
time
why
you
angle
tried
this.
to solve it?
Like that.
So, I mean, I submitted it. It was Saturday or Sunday. I don't know which one. But that's when I originally tried to submit the answer.
Then did you try again?
There's no reason to try again if you think you submitted it.
I didn't.
Oh, you thought you submitted it?
Well, I mean, like, we all submitted it. Like,
Does it? But it comes back with something. They're
Yeah,
not going to.
it did. It says like when you press submit, like, it gave you the feedback that I have.
It gave submitted it, and then you don't see a
I just looked
grade.
at my grade book actually right now. I thought I didn't have this issue, and I looked at my grade book right now. And
That
it
is
was
weird.
submitted.
Okay.
So I was worried now because I don't know, like.
Okay. I will. All right. That's kind of interesting. So that was for quiz 3. Because I'll show you here. I mean, if you come for a moment, there are people who have submitted, and I don't know, because it's not just one person. I think you're 5 or 6, all right?
Yeah.
Unless you said you received it.